So I'm Doug Sibley with Cisco Talos. We're going to be looking at a self-supervised approach for learning embeddings on arbitrary byte sequences today. So I actually want to start us off with an NLP from a couple of years ago. This was from OpenAI, and this their blog was a unsupervised sentiment neuron. So what they did here was they had a corpus of reviews from like Amazon, and they trained a recurrent neural network to predict the next character in the strings. And what they found after doing some deeper analysis was this network actually learned the concept of sentiment during the unsupervised phase. So they didn't even have to train the model on sentiment afterwards. So what we're seeing in this visualization here is the sentiment learned from the training approach. And this is actually really nice, right? We're just trying to predict the next character in text. It's a well-constrained learning task, and we're learning this kind of high order abstraction of sentiment from it. And how they actually implemented this is a little more interesting. They just took raw UTF-8 bytes as input. So they were not predicting English characters. They were predicting the next byte in a byte sequence. So one of 256 values. So we could run this approach on any sequence of bytes, and hopefully it would learn some kind of higher order feature from it, probably not on encrypted data. Their model, when they released it, had 85 million parameters, and it took them 1 month across 4 GPUs, training at about 12,500 bytes per second to get to this result. So it's very nice that this kind of self-supervised approach was powerful enough to teach it, but I don't have a month for models. So the kind of point of this is, can we get the same benefit, but can we do this faster? And so if we want to do this faster, and we started with RNNs, the questions becomes, can we replace recurrence with convolutions? If we can, we get to go a lot faster. We have some nice things like more control over receptive field. And there's already been a lot of work across the industry to make convolutions faster. So we can just kind of hook our cart up to that horse, and we're off to the races. So the short answer in my title, obviously, yes, we can do this. So what does this look like? We give it an input byte sequence of arbitrary length. We want to predict the byte value at every position in this byte sequence. And so that'll be our training task. The model I'm about to describe to you is going to be a model with about 710,000 parameters. And when you train it on a single V100 GPU, it can have a training throughput of around 2.6 megabytes per second. On a 16 gigabyte memory model, we can train on individual sequences up to 800,000 bytes in length before you start running into memory constraints. Obviously, if you have more memory, you can extend this. There's other tricks you can pull here. We could also extend this to be semi-supervised. So there's going to be a point where we have a convolutional neural net. You could throw a supervised loss on top of it. We're not going to explore that here. Anything for the neural net is going to be completely unsupervised training. And what this model is going to let us do is we can produce an embedding kind of for each byte in our sequence, or we can produce a fixed length feature vector from a higher order CNN to take a variable length byte sequence and get a fixed byte representation for it. So quickly, how we're going to do this with convolutions, an important part of this is going to be temporal convolutions. If you look at the top here, this is kind of a traditional 1D convolutional approach, where as you stack layers of convolutions, you're going to have a receptive field spreading forward and backward in time. When we use temporal convolutions, we're going to constrain that so that it only is looking at data prior to position T at every T in the sequence. And you stack this, and we see our receptive field grows over time. And so this is going to replicate in an RNN when you're doing next byte prediction. You can't see the next byte if you're trying to predict it, because the network will just predict what it's already seeing. You don't actually learn anything. So we're going to use stacks of temporal convolutions as kind of the backbone of this approach. Just a couple other things we're going to do with the convolutions. We're going to use densely connected convolutions, which is for each layer, you run your convolution, and then you append that output to its input. So as you stack layers and layers together, each layer is going to see the outputs of all prior layers. You're going to pay a little bit of computational cost here, but it actually works out really well for kind of training good representations. And we're going to throw a little bit of dilation in, which lets you expand the receptive field of a given layer without necessarily having more parameters. So the design of this network, we're going to go into these components a little more, but first off, so an autoencoder is an encoder component and a decoder component. So we're going to look at two things for encoding. First, there's going to be a local encoder where we're going to take our byte sequence, and we're going to run 2 temporal convolutional neural nets on it, one running each temporal direction. And this produces an output that's the same length as our byte sequence. We're going to take that output and pass it to a global encoder, which is a more traditional 1D CNN, which runs through several layers with some max pooling, and you get a fixed byte representation. And our decoder will then take as inputs this local and global embedding and attempt to predict our bytes. And this leaves us, when we get rid of our decoder, we'll have a local embedding model, which can embed each byte in our sequence, or we have a global embedding model, which again is a fixed feature size, which is mostly what we're going to look at in this talk. So the local encoder, this is the starting point in our neural net. We're going to take, first off, we have our bytes. We're going to embed them into a length 8 embedding vector, as one does. We then have 6 layers of temporal convolutions with widths of 15. Each layer has 16 features per, but remember, since we're stacking these together by the deeper layers, its input is quite large. So we kind of need these smaller feature maps per layer to keep the computation down. And we throw in a little bit of dilation here just to expand that receptive view. And we want to run basically 2 6-layer temporal neural networks at the same time. We're going to run one in one temporal direction, and we're going to run one in reverse temporal direction. And as long as you line those 2 up, you can take both of those as output, and that is your output for the local encoder. And you have to line these up correctly. If your temporal convolutions are not aligned correctly, you're going to short circuit your network. We'll test for this later. And we take both of these as the final output. The global encoder takes as input the output from that prior step. We run it through layer norm just to make it a little friendlier. And then we're going to have 9 layers of these dense style convolutions with width 7, 32 features per layer. Again, stacking. We have some strides and some pooling, throwing in on specific layers, and a little bit of dilation as well. And at the end, we do global max pooling across the entire sequence, and that gives us this nice fixed feature vector. And the important part of this was to just get that fixed feature vector size. So I chose to go with kind of a deep pooled design, but things like Malcolm, which is kind of a more shallower but broad, this would also work in this approach. I've had some success with deeper designs like this, so I chose to go with here. It was not super critical to go with one over the other. We just really need this fixed representation size. So our decoder is going to operate on a couple inputs. We're going to have the local embedder output and the global embedder output, which we broadcast back to the shape of our input. And I also add one special convolutional layer here, which is width 17, and it is constrained such that at position T, those weights are always 0. And what this means is this single layer basically can see 8 bytes into the future, it can see 8 bytes into the past, but it cannot see its local location. So it can't learn to just represent what it already sees. And from there, we take a traditional dense network. So it's going to be 4 layers, 64 features. Your final output gets you to sequence length by 256. And you can then directly calculate your cross-entropy loss at each byte position, take your average. This is your training loss. So as I said, this model as described, 700,000 parameters, 2.4 megabytes per second of training. You can shovel bytes through this and it'll at least produce heat. The important part is this actually going to do anything useful, which is where we're going to go with this talk now. So how do we evaluate the utility? Are we accomplishing anything here? So we're going to go through a couple of tests, and all of these tests are using the same model hyperparameters, the same model as described, same optimizer, and we're going to train different models, but we want to just take the same design and see how it does across a couple different tasks. So the first task is the implementation correctness task, which makes sure I don't come up and give a really bad talk to you by having bad results. And the idea is we're really depending on these temporal convolutions to be lined up such that at each position in our byte sequence, we are looking forward in time and we're looking backwards at time, but we're not looking at specifically what we're seeing at that position. Because if you ask a neural net to recreate its input and it can see its input, it very quickly learns to just return what it can see. And this is very easy to test for. You just generate random data, random bytes. And if you have an accuracy greater than 1 over 256, you have some sort of information like somewhere because you're doing better than random on random data. So fortunately, this network as described does pass this test. But this was very useful during testing to make sure your implementation is correct, because it can get a little weird. You can run a neural net which produces output, but it is logically broken because maybe you have a typo somewhere. So since we started with a NLP task, the next thing we're going to evaluate is kind of a analog to that. And we're going to use Wikipedia XML dump data on this. So Wikipedia has obviously articles in a variety of languages, and they export dumps of these from time to time in an XML structure. So this will be the full text of articles with XML metadata about the submitter and all sorts of things. And this is nice because it's kind of a mix of two kinds of data types. We have natural language in articles, and then you have kind of more programmatic generated content. And so in my mind, this is like analogous to system logs or something where perhaps you have a lot of this data, but no one else has any of this data. So you are interested in training unsupervised models here. So for this experiment, we collected about 1 gigabyte of bytes for the English, German, Greek, Hebrew, Japanese, Russian, and Chinese languages. The OpenAI task was just on English. So part of this is we want to see, is this a fluke for English only, or do we do okay on other languages as well? And since all of our data, or all of these data sets contain XML and natural language, we want to make sure the model is not just learning the XML. So what we're actually going to do is take the English model, and we're going to test it on all of the other languages. And that'll show us if the language specific model is doing any better than the English model, which probably shouldn't know about the languages. For this, we just care about the accuracy of the reconstruction. So we're just trying to prove that we're doing better than random guessing here. And this is an example of what the wiki data looks like if you are actually decoding it, right? So we have your kind of XML with, which is obviously English characters, and we would expect to see a lot of this structure repeated across all of the data, but then you get into the actual text content that is going to be natural language here. So it's a nice mix of both. Here's our results for what we do when we just train these models for byte reconstruction. As you can see, each individual language model is doing, I would say, quite skillful at predicting the bytes in its sequences. We're ranging from 70 to 80% accuracy, which is much greater than 1/256. So we're clearly doing better than random guessing. And when we take our English model and we cross-check it across the other languages, we can still see there is a lot of probably XML content in here that the English model knows about. But if you especially look at Japanese and Chinese, you'll see that the English model is doing quite poorly on those, which you would expect. And this is mirrored in OpenAI's results, whereas if you're training unsupervised models on data, transfer learning is a bit of a thorny proposition because you're transferring into some other distribution, which may or may not be quite as related as you think it is. So the NLP data was kind of like our best case scenario for a one-dimensional convolutional neural net. Next, we're going to challenge the model with something that it should not be quite as good at. And we're going to use the MNIST data set for this, which is two-dimensional images. It's 28 by 28 grayscale handwritten digits. So we know concepts exist in this data, the concept of a handwritten digit. But it's not clear if a 1D CNN is going to be able to do anything useful for this. So we're going to challenge the network that way, and then we're going to challenge the network even more by representing this data in a couple formats. The first format is the idealized format, where you just take your input and you flatten it, and you get a fixed length 784 vector for basically NumB, where each byte is 0 to 256 for its brightness value. And so this is always fixed. So at least our vertical features are going to be consistently aligned in the bytes. We can also take these images and save them as PNG images, which is a compressed but lossless format. When you do this, you now have a variable length byte sequence, which is around 250 bytes per image. And then we can also do this with JPEG images, where we're going to save it in a lossy format, and it's slightly smaller. We're down to about 233 bytes per image. So our training here is going to be taking the MNIST training set and doing the self-supervised reconstruction on it. And we're going to look at the accuracy of how this goes. So we can see a couple things here. First off, the ideal accuracy, if we just look at general accuracy, is quite high, suspiciously high, what we see. And then as we challenge the network more with more challenging representations, our accuracy decreases. What we're looking at in the second column here is non-zero accuracy, where if we go back and you look at the MNIST images on the right, any pixel that is black is 0. So when we look at our accuracy for ideal at 88%, we're predicting a lot of zeros correctly, which is good, but is not interesting. So non-zero accuracy is reporting our accuracy on predicting byte values that are not 0. So for our idealized data, this is actually more of a regression task because the pixel value is brightness, but we're still tracking this as accuracy. So if the network predicted 253 as the byte, but it was really 254, that is an incorrect prediction, even though in a regression task, we say that's pretty good. So first off, the ideal format is pretty easy to reconstruct comparatively. And as we get more challenging, we have a harder and harder time. But reconstruction is not what we care about. It's just kind of what's driving the training process. So are we actually doing anything useful? We're going to evaluate this by training our autoencoder. Then we're going to take the MNIST test set and run it through the embedder to get a fixed length global embedding out of it. And we're going to pass this to a random forest to just train a model to predict the digit. We're not back propagating anything into the deep neural net. So that again, it's all unsupervised. But we want to use those embeddings and see if they've learned anything interesting, and we hope they do. And one of the things we're going to do here to kind of double check is we're first going to train these models on an untrained version of the encoder, and then we're going to train a model after we've done this unsupervised training. Now, if the self-supervised task is learning useful representations, we would expect that our model is more skillful after training. If we're only doing good because our model is like functioning as some sort of extreme learning machine, then the training isn't going to do anything for us. So we want to make sure that the training is actually worth the compute. And we're also just going to compare a direct model to random forest on the pixels to show, are we actually beating state of the art? Spoilers, we are not. So what does this look like? First off, the direct pixel model down at the bottom, that is a 95% accuracy. As you can see, none of our models are approaching this. So people have said this in other talks, and you hear it all the time at machine learning conferences, not a silver bullet. Sorry, we all still have jobs. Representation matters, right? It's important to represent your data for machine learning in the best format that you can come up with, but we also live in the real world and we kind of have to deal with things that are not so nice. So there is no equivalent direct pixel representation when you're dealing with JPEG or PNG images. What we're seeing just for general accuracy is our ideal data, again, seems to be the easiest to represent. And as we go to PNG and JPEG models, it becomes harder and harder to learn a good model. However, you'll recall that our JPEG model only had a 7% reconstruction accuracy, which was low compared to the rest, but we're still training I would say, a decently skillful model. If I'm in a room somewhere and someone says you can have a 50-50 model or you can have nothing, a 50-50 model is okay, maybe in some contexts. And we also do see that our untrained accuracy is doing better, right? So especially on the more challenging formats of the PNG and JPEG images, when we start from an untrained version, our accuracy is pretty low, especially PNG. Just by doing our self-supervised training, we are able to uplift the learned representation to kind of have very meaningful improvements in results. So that's a good sign that it is worth the time to do this. So we've seen it works in a couple of contexts. Now let's try it on a kind of more challenging context that is more relevant to us, and that would be the Sorrel malware samples. Sorrel is 10 million public PE binaries and their associated Ember features. And so we can do the same task here. We'll train a autoencoder on the first 1 million samples from the malware data set, which is kind of the oldest samples in time. We then jump forward a little bit in time and pull 200K out, run those through the embedder, and then we again go to a random forest and train a model to predict the malware tag associated with that sample. We are going to train 3 models here. First off, we'll just use the Ember features to see how they do. Then we're going to use just the autoencoder features, and then we're going to use a joint model, which has access to both of those data. And we're going to use the same size random forest here. So it's a toy model, but it should have consistency. Oh, and we did not specifically go after this, but the Sorrel model itself had about 17% accuracy on byte reconstruction. So better than JPEGs, worse than NLP data, seems okay. And here are our results. So the column in the middle you can see is our autoencoder based model is doing about as good as Ember. So just from learning to reconstruct, we are learning features which seem competitive with human derived domain expert features. When you look at these numbers some more, you start to realize they're suspiciously close. I'm assigning this to label noise in the data. So the actual malware tags associated with individual samples were themselves derived from ML. So this is not a perfectly clean data set. I'm not up here saying that my features are better than the Ember features. They are certainly quite different, and they are competitive without requiring that domain expertise. And we can actually confirm this using the joint model. So we took, after training, we take the joint model and we look at the feature importances that it learned from all of the Ember data as well as the autoencoder here. I've broken them apart. Higher is better for feature importance. So we can see there are certain sections from the Ember features that are quite important, like some stuff in the general. There's something in the header that's super important. And then we can see over at the end, our autoencoder is consistently doing pretty decent, I would say, right? It's important enough. We're doing better than some sections, worse than the others. But for this particular model, at least, 43 of the top 100 features, as reported by the model, were from the autoencoder. So again, it's not necessarily that we're doing better here, but we are quite competitive with the Ember features without requiring that domain expertise. And so that's kind of the core idea here. This idea of byte reconstruction appears to be a useful self-supervised task that you can just kind of churn on bytes, and it is learning interesting things, not just on toy data sets, but also on data sets we kind of care about. Byte reconstruction, there's a very large design space here for neural networks. The network as described here is just kind of the approach I usually go for 1D CNNs. I'm not saying that this specific model is the best version. I did not test these hyperparameters very much and still got decent results out of this. Your model design is really just constrained more about training or inference throughput versus your data rates. So this model on a single GPU was 2.4 megabytes per second. Sorrel, if you want to train on all 10 million, is like 8 terabytes. So you do some sort of math and you're like, well, we have this much time. Okay, so maybe you do multi-GPU, or maybe you do a smaller network. But kind of your constraint here is how fast do we need to process versus how much data do we have. And again, we can't get away from feature engineering. If you can sit someone down and engineer good features, you're going to get good results. But on like the Sorrel model, in 2 or 3 hours of training, we were producing skillful models that were, close to human expertise level. So you could go to lunch and have this running on your GPU and come back and maybe have a model that is decent for you if you don't have the benefit of something like the Ember features on your specific data set. Thank you. Any questions?